Hello guys, and welcome to Staad.Pro. This is part 5 of this 7-story building. So we are going to continue from where we stopped last time. But if you are yet to subscribe to my channel, please, I beg you, just click the subscribe button there and hit the like button as well. Okay, I also have an ultimate Staad.Pro tutorial which has pre-recorded videos for 12 days. To just take you 12 days to learn Staad.Pro. I packaged it and arranged it for just 12 days. Every day, each day has a particular video to it. So it's a pre-recorded video. So if you want to get that particular tutorial package, the link is in the description. Just click the description, follow the link and get and procure it. It's not expensive. But so as you are going through the training, you can also be contacting me on WhatsApp. My WhatsApp contact is also in the description, so that we have a seamless learning. So I will be with you, I will guide you. I have so many bonus packages included in that video. Like we designed a real life duplex. You know, everything about the duplex was designed. We also did a steel structure. The tutorial video covers, the training covers both steel and concrete. Designing concrete with RCDC software, which is also part of Staad.Pro, but it's a different software, but embedded inside Staad.Pro. We also did foundation design. So it's not something you're going to miss. You don't want to miss it. If you want to be very strong and sound and build up your confidence in the usage of Staad.Pro, that course is for you. Just get it. I'm going to be with you. We're going to be talking. Even if you need a one-on-one discussion on a particular challenge you're having during the training, I'm always available. You can do a one-on-one. You can do it one-on-one, through any means that we can find easy for us to use, be it a Google video or Teams meeting, or even if it is WhatsApp, anything. So just get it and we talk. Thank you very much.
So in our last class, we were able to apply some primary loads. The self-weight has been applied. The slab dead load also applied on the floors where we have slabs. The partition wall load is also applied. The finishes, we apply finishes as well. Okay. Then life load on slab is also applied. So from the list of loads we are supposed to apply on this structure, we have applied the structure self weight, the slab dead load, partition load, finishes, life load on slab. Then the remaining ones are overhead water load and wind loads. So like we demonstrated last time, from the architectural drawing we saw a tank at the rooftop. So that tank is an overhead water tank, so it's going to have water on it. So the weight of that water, we need to apply it on that floor, so that we take account of it. Okay, so if you look at the architectural drawing, you see this tank here. So now this is where I need to communicate with my client. So I've called him and I've discussed with him about the size of this tank. So he said he's looking at a 1,000 gallon to be mounted here, 1,000 gallon. But in my design, I will give a free board of 500. I will make it a 1,500 gallon. So if this is the kind of tank stand they are going to build, of course there is no space to add another tank under. Yeah, so it's going to be only at this level. So assuming they have a tall, there's no need to have tall tank stand. Okay, so it's just going to be here at this level. So it's going to be one tank. So since he's planning to put up a 1,000 gallon here, in my design I will consider 1,005. So what we do is we convert 1,500 gallons to cubic meter. So you can use Google to do that. Okay, you can ask Google to convert gallons to cubic meter. That's there. So 1 gallon is 0.003 cubic meter. So I'll put 1,500 here. So we have 5.678. So I will take 6. I will approximate to one whole number. So 6. Okay, so then let's go back to our Excel sheet. So we want to calculate the water weight. Bring that one here. So I will make this one bold. It's bold. Okay. Size of tank or capacity. Tank capacity. You can call it P. Is equal to 1,500 gallons. Which is equal to 6 meter cube. Yeah, so this is what we have. Then we bring in the unit weight of water. Unit weight of water you can call it G or gamma, but let me use G. Is equal to, that's 9.81. So what, approximately 10 kilonewton per meter cube. Okay, so the next one is to get our kilonewton force. So we have the volume in meter cube and we have a unit weight in kilonewton upon meter cube. So when you multiply these two, this meter cube will cancel the other meter cube and we are left with kilonewton force. So now weight of water, total weight of water let me call it W, is equal to, I would say, P multiplied by G. This is exactly how to develop Excel template. So if I have a similar project now, I'll just use this template for it. I'm already showing you how to do that. Okay, so I will multiply P, which is 6 by 10. So I have 60 kilonewton. So this is the total weight of water that is coming down on that floor through 4 legs of water tank stand. We have 4 legs of water tank stand. So this the total weight here is 60 kilonewton. So like I mentioned before, I created a node here and a node here. So we already have a node here and here. So this 60 kilonewton, I'm going to be dividing it by 4 and apply that load on these nodes. Let's go to the model. Okay, let me show the last floor for clarity purposes. So I'll select this level, view, yeah. So I created this node and that node, this one, for that purpose. So when I divide that load by 4, I'll apply the nodal loads on this node. So let's do that quickly. So nodal loads will be equal to this W over 4, which is equal to this divided by 4, and 15 kilonewton. So let's create that primary load. Under loading, just click here, add is a live load. I explained it in our last class that the water load is live load because at some point there won't be water in the tank, and at some point the water will be halfway, at some point the water will be full. So it's a live load, it comes and goes. Yeah, so it's not a permanent load. So I'll put water tank load. That's live load number F load number 2. And click on add. And go and add load. Look for nodal load. This is nodal load. The direction is y-axis minus 15. You can also apply Rattler forces, FXFZ, even moments can be applied, and I will select the nodes. Okay, so select on the load, then select the nodes. The nodes are this point here. Somewhere here, here, here. Yeah, so I'll click on assign to selected node. Yeah, so this is our the load of water coming down to that floor. So we can reduce this load diagram. Go to label, under scale. We can just play with this value. Let me put 10 points first. Apply. Exactly. Then we can as well show the value of the load under label. load value, apply. So see the value of the load. Okay, so this is the load we're applying. Yeah, so we move to the next line of action, which is the wind load. Okay, for the wind load, there are two ways to apply wind load. Either you do the wind load calculation and apply it on the members, or use auto-generated wind load and apply it. For the auto-generated, it is the American code that supports that one. So you just use American code and do the auto-generated and apply your wind. Then if you are doing the manual calculation, you can use either any of the codes that you prefer. So for me, I will use American code to generate the wind load and apply it there. So let's show the the whole structure, then go back to our loading. Okay, I'll create a new load. This one will be wind. In this case, call it wind in positive x direction. Do wind in positive z. If you like, you can do both positive x, negative x, positive z, negative z. But mind you, in your load combination, no two wind loads shall be found in one load combination. Because you cannot be the wind effect on a structure cannot be coming in two different directions. It can only be one direction at a time. So if you have four different directions for your wind, it is one wind load direction at a time when you are doing load combination. You have to take note of that. I'll click on add. Okay, so we go to definition, click this plus sign here. Under wind definition, we click on add, then type number 1, comment wind 1 code. So from that here we select the code that we want to use. So we use this code ASCE, like I said before, is American code ASCE 2016. Then I'll add, close it, then select what you have added and click on add again. We come down to exposure condition. Here we put 0.8. Now add. Okay, then select on this and apply it to view, to all the nodes. Then go back to this, click add. So under here you click on generate the active code. She's going to use this code to generate the wind loads. So click on generate. Then from here we select the parameters. So building classification category, is it category 1, category 2, category 3, category 4. So when you check your code of practice, the 7-story building, which is for family house, the residential building, the category it falls on. Then basic wind speed, you have to be careful to note the active unit. So I'm going to be using meter per second. So I'll use 36.5 for this. Exposure category, now you see structure type. What this exposure category is under your code. Structure type, building structures. Yeah, that's building structure. You have chimney, tank and similar structures, solid signs, open signs, lattice framework truss tower. So it's a building structure. What is the height of the building? Height above sea level in meters. So on that one, our height is 20 point something. I think it's 20.6. So just put 20.6. So in this case, the wind load is critical because of the height. Okay, so at this, after doing all this, you click on apply. When you click on apply, you should also check again. Some of these values will change to default 36.5 and click on OK. So you see the load has been generated at different heights. So when you click on the different heights and the load effect, so I'll click on add and I'll close. Okay, we have not finished, so we now come to wind load in X direction. Click on add and come to wind load here, select that. So select type as what is active already. This is the X direction windward face. So we need to now feed in the range values as we did when we were doing our this thing. But this one is going to be simpler. We just need to get the minimum and maximum values. So for Y range from 0, to start from 0, apply the wind load from 0 point to the last point, which is 20.6. So I can just put 21. For X is still from 0, so I can't remember the width of the building. Well, it's not up to, I think it's 10, so we can put 12 here. This one is from 0, I think, to 16, 15, thereabout. Okay, so if it's an open structure, you check this box, so that if it's an open structure, of course, you know the wind load will go in through to affect all the members within the structure. Or if it's not an open structure like this block one, the wind load will only affect the surface area. Yeah, the surface area, the outer walls. That's where the wind load will be hitting, to be hitting an area. But when the structure is open, the wind load goes in through the building, passes through the building, thereby affecting all the members. So in this case, is not an open structure. So we click on add. Okay, so when you click on this, okay, we can actually change the scale of the graph so that we can see it clearly. So you right click and select the labels, and under scale we play with this figure, distance and points. Let me check this one, 1 and apply. So this is our wind load in X direction. Okay, so it's not supposed to be affecting this side, so I need to check the distance in my Z direction and reduce it, so it shouldn't be affecting here. So let me quickly do that. Let's go back to geometry. Okay, go to view, select this floor, view again, okay. So our dimension from here to here. That's 14.8. Okay, so let me go back, review whole structure. Go back to loading. So we can edit this actually. So I'll put, let me just put 14 here and see what will happen. Yeah. So now, but okay, 14.8. Okay, 15. Okay, the cost, the problem is because of this curve. So if we don't include the total, this it will not affect the curve, this curved part, and this place will not be affected as well. But when we try to limit it to that place where we have curve, you see what's happening. So I will just leave it like that. That's what stays for me. Let me leave it like that. Yes. Okay. So we go to the Z direction, do the same thing. Under wind load, this time around we put Z, then our range is, so if you want to do the negative side of it, when you choose negative X, make sure that this factor is minus 1. That is what changes the direction, not this one. So I'm doing positive Z. So from 0 to 21, from 0 to 10, 12, from 0 to 15, click on add. So that is it. That is it. So let me view and see what we got there. Okay. That's that. So with this, we are done with the wind load application. We are done with the wind load application. So we go into load combination. So we go back to the loading. Okay, so your load combination you have to do it in accordance with the particular code and standard they are using. So this combination I'm going to do here is going to be based on Eurocode standards. So if you are doing American code, the only difference is the load factors. So in Eurocode, when you are considering ultimate limit states, the dead load is being multiplied by sometimes 1.2, 1.4, then life load 1.6. So in Eurocode, we have multiply the dead load with 1.35, while the life load is 1.5. So these are these little differences, and there's a way American code do their own combination, then Eurocode there's a way they do their own combination. Just use your particular code. If you're using Indian code or Canadian code or any code you're using, check the code and see how, what is applicable in their own pattern of load combination, and apply that when you get to this stage. But for this one, I'm using Eurocode for my client. Okay, so I'm going to be considering the 4 load combination types. The first one is going to be SLS load combination, that's serviceability limit state. Serviceability limit state combination. Then the second one is going to be equilibrium load combination. The equilibrium load combination is a way you try to destabilize the structure, maybe by reducing the self weight by with a factor of 0.9 and applying the wind load to see how to test the stability of the structure. So that will help us to do our foundation. It will help us to generate a lot of overturning moments, like sliding forces to enable that we will use to check our sliding and overturning of the foundation. Okay, so now the other one is ultimate geotechnical. That one is for the geotechnical design, the foundation design itself. So geotechnical load combination is where we get the parameters for our geotechnical foundation. That's the design, foundation design. Then the fourth one is structural load combination. So that one is for member design. So structurally, how the structure reacts. That's where we use the maximum load factors, for us to have member design to be able to withstand the forces, when they are increased with those factors. So let's dive into it. The first one is going to be SLS combination 101. This is my pattern of numbering. Yes. Then I will combine all the dead load from beginning to end with load the factor of 1, add date, and 102. Okay, I'll combine all dead load and live load. Everything is factor 1. 103. All dead load, live load, and one of the wind loads. Yes. 104. All dead load and live load plus the other wind load. This is why I said the two wind loads cannot be acting at the same time. So it is one direction at a time. This is what I just demonstrated now. So add this. So with this I'm done with the SLS combination. So I will move to equilibrium. So call it equi combination 201. Because it's second level I used 200. The other one was first level 100. So the third one will be 300. The fourth one 4. That's my own way of numbering them. You can choose your parts. It's not as per code. So this equilibrium combination, my dead loads, I'm gonna be reducing them by a factor. So this place will be 0.9. You can copy this, paste, 0.9. So I might not include my life load because life load helps to even stabilize the structure. So I'll just assume the structure is less than its actual weight, then I'll apply wind load to it and see how it's going to react to that. So I will apply this wind load here. Click OK and add. Do the same thing but with the other wind load 0.9. This is 202. I'll add. Okay, then I'll go to the third one, which is geo combination geo combination 301. So for geo combination, all the dead load multiplied by 1, then the life load will be 1.3 as per Eurocode. Okay, I'll add dead load 1, life load 1.3, wind load 1.5, 1.3, sorry, everything is 1.3. I need to edit this name. 102 modify. Okay, then I will do the third one. 103 303, sorry. With the other load combination, wind 1.3, 0.3, 1.3. Okay. Sorry, I need to. It's asking me to modify. I'm not modifying. I need to. I'm adding a new one. Yeah. So 303. The last 1.3. 0.3. Okay. Then the fourth one, STR, as structural combination 401. In this case, you can combine all the dead load 1.35. Copy this, all the dead load first, then all dead and life load for 402 1.35 1.35 0.35 0.35 1.5 1.5. Add paste again 403 all the dead load, life load, and one of the wind loads. So this one is 1.5 0.5 1.5 1.35 1.35 0.35 0.35. Okay, so now if you are doing a project for a company and your design is going to be reviewed, you have to listen attentively. It's going to be reviewed by another designing firm, consultancy firm, has um, a good and quality engineers. So in combination like this, when you have wind load and life load combined together, one is critical, one is not critical. The designer determines which one is he considers to be critical. So you might not use 1.5 to multiply all throughout. There is a factor as recommended by the code that you can use to multiply one of the, maybe the wind load or the life load. So when you multiply, if you choose to multiply with by the life load, I think the factor is 0.5 or 0. I think 0.5. When you multiply 1.5 by that, this factor is going to be reduced, by 0.75 or 0.65, something like that. So you put that factor here, while the one you consider critical at that moment will be the one with 1.5. When you are done with this one, you can change it and do it the other way. You get, because it's part of what these people might be checking. But for me in this case, my client doesn't even have time for all these checks. But what I know is that I have to give him a design that will not fail. Yes, so for me it will give me the maximum forces for my design. Yeah, so that's that. So when you pick up your code, you look at the load condition aspects, you see all those factors and apply them accordingly. Okay, I'll add in the last but not the least 404. So we have all the dead load and life load, then the wind load from the other side. Okay, this is 1.5, 1.5, 1.5, and the rest is 1.35, 1.35, 1.35, 1.35. Okay, so that's the end of our load combination. So the next one is analysis. We are going to dive into analysis now. So for us to do that, just click on analysis and design. So we get to this place, we click on this define commands. Without defining command, the analysis will not run. So here is asking us to print, giving us print options. So you can choose this first one, which is no print. The second one is load data, and the other one is statics checks. These are the things that when you go to output, start output, anything you select here is what you are going to see there. So for me, I usually use all. Let it print all. Yes, print all. Then you click on add. So because of this command here, our analysis will now run. Perform analysis print all. So we haven't done that, we now come to this place and click on run analysis. So you say yes, save and run. Okay, if at this point you've learned something, I will ask you to subscribe to my channel if you have not done that, and give me a thumbs up. Okay, here we have two errors. We have two errors, 0 warning and 2 no. So we have an error in our model. That's good. It is also good for your learning. Let's debunk this and find out what the error is all about. So now, I told you before initially that when you have an error in your model, you're not going to have any output. The structure is not going to run to the end. You're not going to have any output. So if you see this place is blank, go to post processing mode is very blank. You don't have any output. So we just go to view output file. From there we can check what the error is all about. We say done. So we come here. You see, it's telling us elastic modulus E not entered for member or element or solid number. So the member number is 483. Okay, a section property not entered for member. So it's the same member 483. So we need to check our model. It's like we did not assign property to one of the members. So let us quickly go to 3D view for us to see which member we did not assign property to. Let us check. Okay, so I have seen something here. So this member does not have property. There is a member here, does not have property. This is it. Okay, let me go to view so that we can see it clearly. I found out the error. So sometimes it happens. So when you do a design and you see an error message like that, don't be discouraged, don't be tired. Just find out what the problem is, just as we have done, and try to fix it. So okay, I'll select this level. This is where I have that error, where the error is coming from. So this is the member. This member here is just a line, so it does not have property. So that's why. So let's quickly assign property to it. Now go to view and view only that level. Isometric. So let us know the okay. So I will assign this same beam to it. Assign. That's good. So let's go to loading and make sure the self weight is also affecting it. So that's just it. Okay, self weight is affecting it. That's fine. Every other thing is alright. Every other thing is alright. So we can now go back to our analysis.
Okay, let's wait for it to come. Another error. So let's check the output to see what the error is all about. Error: corp member has non-uniform load specified. Okay, this will now take us to the next class. We are going to solve this problem. I actually want us to solve it because curved beam have limitations in Staad.Pro. So it depends on how you get your curved beam. If you get your curved beam the way we did using the curved beam icon in Staad.Pro, that particular one has limitations. It doesn't accept uniform load, like area load or floor loads on them. They only accept member loads, the member loads. So but when you now get your curved beam with normal beams, by creating nodes and you join those nodes to create a curve, it's just a normal beam. It can accept anything. So by next class we're going to modify this structure and fix this error. Stay tuned and subscribe if you have not done that. Share this content and have a nice day. Thank you.